All right, today we are getting into something that is absolutely critical in chip design, but, sometimes it gets a little overlooked. We're talking about grid check analysis. Think of it as the health check for your chip's power delivery network. It's the foundation that literally everything else is built on. Let's dive in. So just imagine this for a second. You spend months, maybe even years, designing this incredible skyscraper, but it turns out the whole thing is sitting on an unstable foundation. That entire project, it's at risk. Well, that's pretty much what happens when you don't pay attention to the integrity of your chip's power grid. A weak grid means a weak chip, and it's pretty much guaranteed to fail when things get tough. And that really gets to the heart of what we're talking about today. Before you even think about doing a complex IR drop analysis, you've got to ask a much more basic question first. Is the power grid itself even structurally sound? That's what grid check is for. It's that first step you just can't skip. So why is this pre-check so important? Well, because skipping it creates this cascade of problems down the line that become incredibly hard and super expensive to fix later on. Let's take a look at what happens when you try to cut this corner. If you jump right into an IR analysis with a weak grid, you're going to see violations just pop up everywhere. The problem is you won't be fixing the real issue, you'll just be chasing symptoms. And that leads to these painful, long debug cycles, sudden and costly design changes right at the end, and you guessed it, major project delays. So a good way to think about grid check is like preventative medicine for your chip. It's this really simple diagnostic that just checks the basic health of your power delivery network. It makes sure power is getting everywhere it needs to go, nice and uniform, and it spots any weak spots or high resistance paths before they turn into a total nightmare. Okay, so how do we actually do this health check? The process is actually pretty brilliant. To figure out what's bad, you first have to define what's good, or at least what's acceptable. And that's where this concept called the reference cell comes into play. Here's how it works in a nutshell. First, the tool takes the entire power grid and basically turns it into a giant map of resistors. Then, for every single standard cell in your design, it calculates the resistance from its power pin all the way back to the main power source. And finally, it compares that number to a threshold you've already defined. So here's the crucial part. How do you set that threshold? Well, that's what the reference cell is for. You basically imagine placing a cell in the most perfect spot possible, right in the middle of a perfectly designed grid with perfect connections. The resistance from that cell becomes your benchmark. It represents the absolute worst-case resistance you should ever see in a healthy grid. It's our gold standard. And yeah, this visual shows it perfectly. See how the reference cell is sitting right there in that ideal spot? It's the same distance D from both the VDD and VSS power straps. And it's got all the right via connections. The resistance measured from that specific spot, that's the number we're after. That's our maximum allowable resistance. After that, the rule is incredibly simple. The tool just goes through your entire design, and any cell that has a higher resistance value than our ideal reference cell gets flagged immediately. It's a failure. It's a really clear pass-fail test. No ambiguity. Now, calculating this resistance, it's not always done the same way. The tools typically use two main methods, and it's a classic engineering trade-off, really, speed versus accuracy. Let's look at the shortest resistance path, or SRP, and effective resistance, or ER. This slide really just nails the difference visually, doesn't it? Over on the left, you've got SRP. It's simple. It just finds the one single physically shortest path from the transistor back to the power source. But look on the right. That's ER. It's way more comprehensive. It's analyzing the entire network and considering all the possible parallel paths that the current could take. And this table breaks it down perfectly. SRP is blazing fast, which makes it awesome for running across the whole chip to get a quick look. ER, on the other hand, is much slower, it's computationally expensive, but it's also way more accurate. That makes it perfect for doing a deep dive analysis on critical areas that maybe SRP flagged as being a little bit sketchy. Okay, so here's the key thing to remember. The effective resistance value will always be lower than the shortest path resistance. Always. And why is that? Well, think of it like a highway. ER sees that there are multiple lanes available, so even if the most direct route has a little bit of traffic, the other lanes help everything flow smoothly. SRP only sees that one direct route and completely ignores all the others. Okay, so we know how to find these high-resistance trouble spots, but what actually causes them in a real design? Let's take a look at the anatomy of a weak grid and point out some of the most common culprits that lead to these failures. Wow, yeah, this image is worth 1,000 words for sure. It's like a gallery of everything that can go wrong.
You can see these broken grid lines, fractured interconnects, spots where the vias are just gone. Now, compare that total mess to the clean, ideal reference grid over in the corner. I mean, the difference is night and day.
Let's break down what we just saw. You can get high resistance just from a bad initial grid design, power straps that are way too far apart. A really common one is grid chopping, where engineers actually cut out pieces of the power grid to make more room for signal routing. And of course, weak or missing vias. Those are the vertical connections between metal layers. That's like having a bridge out on your power highway. All right, we've talked about the why, the how, and the what not to do. So let's bring it all together with the one single most important thing you need to remember from all of this. If you take only one thing away today, please let it be this. Do not waste your time analyzing power drops on a broken foundation. Fix the grid first, always. Then, and only then, should you run your IR analysis. Because when you follow that one simple rule, everything else just gets easier. A solid, healthy grid means you're going to get predictable IR behavior. Your debug will be faster, your results will be way more reliable, and your whole path to getting that design signed off becomes so much smoother and more efficient. So I'll leave you with this thought. That choice between SRP and ER, it's not just a technical decision. It's a strategic one about how you manage risk. When you're staring down a deadline on your next project, are you going to go for the fast, full chip scan, or are you going to opt for the slow, super accurate deep dive? The health of your chip's foundation really depends on that answer.